Okay, sorry guys, we got cut off in the last video. I reached my time limit. So picking up where the last one left off, discussing some other equations. So just real quick, frequency and time period are inverses of one another. And this equation right here, V equals frequency times wavelength, F times lambda, is kind of like as simple as it is, one of the most important wave equations, sometimes just called the wave equation. And we could figure, if we know the frequency and the wavelength of the wave, we could figure out how fast it's traveling. Now, what does that mean, how fast it's traveling? That's really how long it takes a point on the wave to get from point A to point B. That's just how we define velocity at any moment, even for like a car traveling this year to get from one point to another. So let's go back to our wave simulator. And let's say the point A is where the wave is being generated, a green dot of this oscillator right here. And let's say point B is as soon as it goes out the window. All right. So if we told you the velocity of this wave was 5 meters per second, just making up a number there, that means a crest that's generated, or anything that's generated at any moment at this point, travels 5 meters in 1 second, right? 5 meters per second. So literally, all the wave velocity means is how long it takes that to get from point A to point B. And there's a secondary formula of the wave equation. If we just do a simple mathematical substitution, if we take 1 over t, the inverse of frequency, and plug it in here, we could get v equals lambda over time period. So remember, time period and frequency are closely related ideas. They're just kind of opposites of one another. And if you know one, you could always find the other. Just units on all these that we typically have them in, especially right now. Frequency is hertz, that was described in the last video. Time is a time, that's in seconds. Wavelength, lambda, that is a length, it's in meters. And v, velocity, like always for everything this year, meters per second is the core unit one. Mentioned this when we were watching the simulation in the last video, that the fact that amplitude is independent of the frequency of the wave. So what that means is, here's a picture of 3 different waves. They differ only in amplitude. You can notice, look, they're lined up vertically. Crest, 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 crest. They all have the same wavelength, because from crest to crest, they all would have the same value. And I know they're not in motion, you can't tell this, but it turns out if they all have the same wavelength, they actually will all have the same frequency as well. But the main point here is I have 3 waves with all the same wavelength, but they have different amplitudes. Those things are completely, amplitudes independent of those other things. Going back to our formulas on the last screen, you notice amplitude was not in any of those formulas because it doesn't affect any of those values. If it affected it, it would have to be in the mathematical formulas. This next will be for the next time. Let's actually go focus on more equations now, because your study guide's going to have this. So the formulas we have, which were already on the notes page, was F equals 1 over T, big T. V equals frequency times wavelength. And the third formula combine those two is V equals lambda over T. But there's actually another one, an old one I use as well. And this goes back to the basic definition of velocity from the very, very beginning of the year. V equals d over t. That's another possibility to get used. We just got to be careful with something, because remember, wavelength, when we're finding its velocity, is really just to be viewed as object getting from point A to point B. or at least a point on the wave getting from point A to point, the energy of the wave going from point A to point B. Where we have to be careful, though, is that both wavelength and general distance are measured in meters most commonly. So you can't get those confused. In a problem, when we read the context of the problem, wavelength, remember, is the distance between any two repeating points on a wave. That's a very specific distance, right? So if you're going to call something in meters a wavelength, then it better represent that. If this represents the distance from some starting point to some ending point of the wave when it was generated, it's just a general distance d, which may also be in meters. A similar thing we got to be careful with these two times. Time period big T and time period little t are two different things. They're not the same thing. Time period, if you recall, is a specific time of a wave, the time it takes for one full cycle or one full vibration, whatever you want to think about it. Little t is just some time to get from point A to point B, right? The wave is generated at point A and it eventually gets to point B. That's what we're talking about for this equation in red. The distance between point A and point B the wave is traveling through or to is just a general distance. The time it takes to get from there to there is just a general time of travel. If we understand that, most of the formulas or problems using these formulas hopefully will be pretty understandable. Now, there's going to be several problems in the study guide I am giving you and assigning with this video, and I would like you guys to try them the best you can. And later in this week, I will post a video going over those problems, not only just giving the answers, but also going over them. But I want you guys to try them first. So I hope this video helps you do the study guide. I will also post the links to physicsclassroom.com where you can read more about it to help you. Like I said, later this week, we'll go through those problems to make sure everybody's on